Perfect. Exactly. And thank you all for attending my presentation regarding reference districts and how one may identify them by using machine learning and open source data. And this work is an extension of the master thesis of one of my students, Thi Thu Ha, and with some help from Schlueter and Kruse from the architectural chair. So, starting with the motivation, on the left you see the big goals of Germany regarding energy transition. And on the right you see some news articles I brought with me. I didn't bother to translate them because I can summarize them in 2 words. How's it going? Not good. Basically, it's very slow. And regarding the obstacles in the building sector, we are facing like 70% of existing buildings that are constructed way before any ordinance regarding thermal insulation or energy codes. Most of those buildings are still heated with fossil fuels, and the renovation rate is quite low. The maximum is, I think, 4%, but the average is 1 to 2%. So changing this, we could either consider buildings themselves, which would incorporate a variety of different tailored solutions, which is very complicated, or we could consider a different scale. So shifting the energy optimization of individual buildings to the consideration of entire districts, thereby allowing for economy of scale to work, reduction of transaction costs, for example, by energy sector coupling. And there you see some pictures of planned districts, as we saw before in the first keynote. This is again Hamburg, so the Elbphilharmonie is very close by, and the general benefit of planning a holistic district is, of course, that all the energy systems and everything is all planned holistically as well. However, if we are considering what is a district, we'll find that for existing districts, it's very easy to identify them because they're constructed holistically. But existing districts or buildings in existing districts, that's very much harder to identify because there are multiple aspects that go into it. So I brought a quote which tries to summarize the complexity of it. A district is a contextually embedded, socially constructed, yet vaguely defined central place of everyday life and individual social spheres whose intersections are reflected in the spatially identifiable context of manageable residential environments. So this very complex sentence also identifies like the problem in the concept of districts, because we have an urban planning construct which is considering the built environment with cultural aspects, so how is a district grown over time, the history of it, and of course the social interactions, so the people living in it and how they are considering their environment they're living in. So the idea of this work is to find an existing building stock, districts, and the question or the proposal and how we could do this. And one further step we want to go is to see if those districts that we find, if we can find more similarities between them and cluster them into reference districts that we may work on later on. So the general idea, the methodology is use open source data, georeference data of the state of North Rhine-Westphalia in Germany regarding buildings and of course energy usage, but also infrastructure. Combine this with machine learning, specifically clustering, to identify very homogeneous reference districts. So a possible energy solution to one reference district could be also applied to another reference district. So reference district is more like a type or a label we want to put on districts that we identify. So features that we are considering for the social infrastructural model is, for example, building density, so how many other buildings are in the near proximity, and of course distances to institutions that are important to daily life, for example, religious institutions, parks, roads, hospitals, and so on. So this is the social infrastructural scale. On the energy side, we want to focus on renewable energy, so focusing to the locations of roof surface PVs, for example, or biomass availability, inside a city. And on the demand side, we are considering building heating demand and the building type. So is it a multifamily house, is it a single family house, and so on. And as you notice, all of those features are capable of to be attributed to a specific building. So this is what we are clustering in the first stage. And it's a multi-stage clustering process. So as I said before, in the first stage, we're clustering the features of socio-infrastructural approach. So considering a feature matrix, each row represents a building and each column represents one of the features. And secondly, the energy features we also cluster separately. The resulting clusters, you can maybe also already call them districts, or at least they could become districts, are then further enriched with the second stage, with the demand features, so the heating demand, and finally we arrive at the big final feature matrix regarding the clusters and try to identify the reference districts from those. And this study is applied to the city of Aachen, where my university is from. So the algorithm of choice is k-means. Basically, each data point, in our case, in the first step, is a building, and in the second step, a cluster, can be assigned to a specific cluster by distance. So it's a distance-based algorithm compared to dbScan, for example, which is density-based. And we chose it because of its simplicity. So there are basically two parameters that need to be hyperparameterized, and one of them is k, so the number of clusters we're actually looking for. And also the interpretability of this algorithm is quite high, so k, the selected k we choose, is actually the amount that we get of clusters. It's very efficient, and with such big data sets of GIS data, it's very important. It's also scalable, of course. And because in the first stage we applied to actual distances in a georeference sense, and in the second stage we applied to differences in heating demands, it's important that it's flexible. And we evaluate it by using the silhouette method. So this is the method basically calculating how cohesive one cluster is, and ranges from -1, poor, to 1, very good. So, coming to the results. The first model, what did it produce? The first model produced 54 clusters with a silhouette score of 0.326, not very strong, but we already can see from the map, so this is a map of Aachen with already the 54 clusters found. You can see that in the first model we have a very big center, and as further we go from the center we go, the smaller and smaller the clusters become. And this should, of course, be obvious because most infrastructure is centered in the center of the city. And the yellow in the middle one, the cluster consists of over 6,000 buildings, for example, while the outskirts only manage building size of 65. And with such different sizes, of course, the heating demand of each cluster is very much dependent on the amount of buildings in it. In the energy model, we find 58 clusters, and here we see already a difference. So the center is much more portioned out as before, the size, so the areal size of each cluster is much more uniform compared to the first approach. And we can see that also the heating demand is now less dependent on the size because it's much more uniform, but more dependent on the building function. So if it's a residential building or office, for example. So after enriching this data with heating demand and building type data, we continue and identify reference districts. 6 of them to be precise. So here you can see in the picture, now the clusters are no longer need to be in direct proximity. For example, if you see the green cluster, you have one close to the middle, below, and one on the right. So now these are the labels that we put on the different clusters we find before, and those are our reference districts that we want to consider and see if one solution to one cluster could be applied to another district of the same type. So, what else can we see? That, of course, like the perception that we get evaluating this, regardless of the silhouette score, is that, yeah, it kind of makes sense. We have a circular pattern around city center. That's, if somebody visited Aachen before, or maybe will, it's very representative of how the city evolved over time. You have the big clustering in the center, where we have the multifamily houses. We have also the university, which doesn't have one campus, but many buildings in the center. And then on the outskirts, you have this little, almost villages with single-family houses. That would be the cluster in red. And some interesting facts is, for example, the similar clusters, that's 1 and 6. So the should be the pink and the blue one, they overlap somewhat, but the difference is in the heating demand, because in the blue one, if you go there, that's the more industrial part of town, so there are much more factories compared to the outskirts of pink, where there's more office buildings. So, what did we learn from our first proof of concept? Feature selection is, of course, very important, and we didn't consider all features we wanted to initially, just because the data size gets so high that it's just infeasible to do in reasonable time, at least for now. So we left out, for example, geothermal data, which is in Germany at least a very important renewable energy source, and we need to work on our feature pre-selection. Validation. There's a discrepancy between the perceived perception and the mathematical validation. So even though the number, the silhouette score, does help somewhat to identify a cluster, but without going actually to the districts and seeing if they're feeling cohesive, it's not enough to have a number pointed to a cluster. Methodology. Maybe starting from a building as the atomic unit of clustering isn't the right approach. Maybe you should go one step higher, so building blocks, multiple buildings of same size and around same heat demand would be a better starting point. And interpretation. So again, without on-site checking, and maybe also trying to produce some of those energy solutions for one district and see how much is it applicable to another, it's hard to say if it's actually worked or not. And the big question, is it scalable? So for City of Aachen, we used the high computation performance center of the university, and for one model it took us about 2 days of computation just to get any clusters. So how much is that transferable to the state of NRW? Is it possible to compute all those clusters separately for a city or a region or a municipality, or does this approach require to actually cluster everything all at once? So this brings us to future work. Those are the areas we want to improve on in the future. So if you have any suggestions, very welcome, and for your questions as well. Thank you for your attention.
Thank you very much. You're right on time.